why I use these extra parentheses. I mean, it makes it so ugly. What happens without the parentheses?
You lose your order of operations.
Yep, the priority of the operations is not clear anymore. Now, in this case, I can actually not use the extra parentheses and it will still mean the same thing. It has to do with the and is kind of like multiplication, the or is kind of like addition. So in normal math notation, you always do the multiplication before you perform the addition when there are no parentheses telling you which way to go, right? It's the same with Boolean logic. With Boolean expressions, we perform the conjunctions first, and then we perform the disjunctions if there are no parentheses telling you which way to go. Do the extra parentheses hurt anything?
No.
Does it make it incorrect in any way?
No.
Nope. So we'll just leave it in for clarity purposes. Are we okay so far regarding the post condition thing? But is that what we want? I mean, does that specify, does post 5 states that z is the maximum of x and y?
It said it could be either or.
Hmm?
It says it could be either.
It's not either or, it is just or. Okay, either or is different. Okay, but does that spell out that, so here's the question. Does post 5 states that z is the maximum of x and y? That's the question. Just because I can derive a post condition does not mean that the algorithm is right. It simply means that this is the end result, but is this the end result that I want? That's the question. Well, let's think about it, okay? What is the property of a maximum? First of all, it has to be the same as one of the original items, right? Is that guaranteed? Yep, it is. Z equals x is on one side, z equals y is on the other side. One of these two has to be true. So I'm guaranteed that z has to be either x, z has to be the same as x, or z has to be the same as y. At least one of those two has to be true. Okay? So that satisfies the first requirement of a maximum. It has to be the same as one of the original items. The second one is, am I guaranteed to pick the one that is larger, if there is a larger one? Yeah, because if x is larger, then this is guaranteed. What if y is larger? Well, then I'll pick this one. What if x and y are the same? This will still be true. So just by analyzing the post condition, we now understand that this algorithm is going to be correct regardless of what you throw at it. You can give it any value of x, you can give it any value of y, it will still come out with the proper answer. Yep?
Yeah, where's the post 5 when it says x is less than or equal to y, you have to include that, or x could be either one of them if they're equivalent?
Okay, are you talking about this expression here?
Yeah.
Okay, we can expand it a little bit. Okay, but this is a little bit, I'm not sure whether this will make it easier or harder. Okay, this expression by itself is stating x is less than y or x equals y. Okay, that's an expansion. Because when you say x is less than or equal to y, you're really saying x is less than y or x equals y, which is it's just a shorthand of that. But you have an or inside parentheses, and then the whole thing is ended with something else. It is kind of the same as something plus something in parentheses times something else. In other words, the distributive law that you know about in arithmetic would also apply here. So we can actually expand the whole thing. If I want to expand the whole thing, it gets a little bit tedious, but we'll just go ahead and spell it out. So if you spell out the whole thing, it really is saying this. Oh, I missed one open paren here. That is the whole thing spelled out. Okay, if you look at this whole thing completely spelled out, does it still describe that z is the maximum of x and y? Sure, because the last one is simply saying, what if both numbers are the same? Well, if both numbers are the same, they're both the maximum, and you can pick either one, to compare to Z. Yep.
That second last and is supposed to be an or.
Oh, it is supposed to be a or. Thank you. This one. Supposed to be or. Thank you. Good catch. Okay. So are we okay so far? Now the derivation is kind of important, but the more important point is why are we doing this? Okay? The reason why we are doing this is without using a single trace, a single test case, by deriving post 5 from pre 1, I have just proven this algorithm is correct. Period. Okay? You can try any combination of x and y, and it is guaranteed that z will be the maximum of those two. Is that significant? Well, for a simple algorithm, may not be that significant. But if you're dealing with a more complex algorithm and you can still do this and prove that your end result is correct, it is significant. Because in that case, you can spend a lot of time, you can spend 2 days to finish the derivations, but that means after those 2 days of derivations of intense math work, there's no need to use any test cases anymore. There's no need to feed it like gazillions of test cases just to see whether it works in all test cases. Okay? Does everybody understand the significance of this type of derivation? Okay, very good. We have about 20 minutes left, so let's go ahead and get started with loops. Now, loops are evil. Okay, let's think about loops here. Okay, so we'll say, we'll do something that's really easy. Typically what a loop does. Okay, we'll say x is less than 3, do 3, x gets x plus 1, y 4, and while. Okay? Really typical type of loop structure. You initialize a counter of some kind. You specify in the loop, as long as the variable is less than a certain amount, stay in the loop. And somewhere in the loop, you say add 1 to the variable, so it will keep incrementing until it gets to the limit. Then the loop should exit, and we're done. But the question is, we all know by the time we exit this loop, what should be the value of x?
3 or 3.
In this specific case, we know it has to be exactly 3, right? The more general way to describe it is x is greater than or equal to 3, but we know exactly it is going to be 3. Okay? So the question is, but what can we prove it? Can we, instead of just tracing it, can we prove that that really is the case? Now, it gets a little bit tricky because of this picture. So we'll go ahead and draw a picture of a pre-checking loop, which most of you should be fairly familiar with at this point. Okay, we have an operation here. In this case, the operation is simply adding 1 to x, incrementing x. And when it's all done, we have to go back to this point. Then we ask the question, if it is true, we go here. If it is false, we go here. The question we are asking is x less than 3? And this is our path to exit from the loop, like that. Okay, do you guys still vaguely remember a picture like this for pre-checking loops? Okay, so let's go ahead and try to identify, the pre and post conditions now. This would be pre-1. The precondition of line 1 is, what do we know about anything before we get into the loop?
X equals 0.
Nope. We say we know. Oh, you're right. You are correct. Okay, stand corrected. In this case, we know that x equals to 0 but it is no longer pre-1. It is actually pre-2. I forgot about line 1. Okay. All right. So that's good. What about this one here? This is our pre-3. Okay, very good. Pre-3, very good. So we are not doing any derivation. We're just labeling, these parts of the picture so that we know when we talk about pre-blah, it is here in the picture. What about this part here?
Post 3.
Yep, post 3. And my pen is running out of ink. I can't find any other ones. I guess this will have to do. What about this part here? That's post 4. Very good. Post 4. Just like that. Well, that seems pretty easy. All right. So let's go ahead and try to derive all these pre and post conditions. All right. So we'll go ahead and start with pre1. So some of these, I'm going to skip a few steps because, it's not the major point of the discussion. Pre1 is true because I don't need to make any assumptions. So I would just say that pre1 is true. Because line 1 is a simple assignment statement, we go from step 1 to step 5 right away, apply the forget operation. Does true mention anything about x? No. So there's really nothing to forget. We get to keep the whole thing. Now this is the part, technically speaking, post 1 is true and x equals to 0. But we can simplify that to x equals to 0. Because true and anything is anything. Not true, anything. True and anything is anything. It is the identity of conjunction. Yep.
Why are you saying that line 1 is true in the first place?
Because we have to state what do we know about the variables. Saying that pre1 equals true means that I do not need any assumptions whatsoever. Okay? All right. So post 1, easy schneezy. What about pre2? Well, line 2 follows line 1. So that means pre2 is the same as post 1. Does that make any sense? Because these two statements are right next to each other. So the post condition of the one before becomes the precondition of the one after. Okay? So that's not too hard, because they're sequential, they're next to each other. Cool, not a problem.
So pre2 would be x equals 0?
So pre2, yep, if you spell it out, it would just be, x equals to 0.
Okay.
Yep.
I still don't understand post 1 why if it's why is it true and x equals 0 still if it's true you know nothing if you do that.
Because true and true is true, true and false is false. In other words, when one side of a conjunction is true, then the expression preserves the other side, whatever it is. Okay? It is almost exactly the same as 1 times k is k, 1 times j is j. So the 1 in multiplication is called the identity of multiplication. True is the identity of conjunction. Okay, true and whatever is that whatever. Okay, so that's all the easy ones. When we get to pre3, it gets a little hairy. And you would say, why would 3 be a little hairy? How many ways do we get to the pre3 part? There are 2 ways to get there, aren't there? Okay. The first way is coming straight in from here. The second way is to come in through here. So there are 2 ways to get to pre3. So let's just look at these 2 conditions and say, well, and by the way, every single time we get here, it has to get past this check too. Okay. So when we say pre3, we have to say a few things. We know for sure x is less. What?
Don't we have to do a post 2 first?
No, there's no post 2 because there's no need to say anything about post 2. It is pre3 is the one that we are after.
Okay.
Okay. So in this case, we know for sure that by the time we get here, x is less than 3 has to be true because otherwise we'll be out of the loop. What else do we know? Well, we know that we can come from either straight in or we can come back because of the loop. So that means we know that x equals 0 if we come in the first time, or this is bad because if we come to this point